Warning: this material has been copied or communicated to you by or on behalf of the University of Western Sydney pursuant to Part VA or VB of the Copyright Act 1968. The material in this communication may be subject to copyright under the Act. Any further copying or communication of this material by you may be subject of copyright protection under the Act.
Okay, welcome back. Isaac has some information about the past session to give to you. Thanks.
Hi everyone, I'm Isaac. I'm doing your past sessions for Maths to Engineers 2. I've changed the room and day. It's now Thursday 1 to 2, so starting this afternoon in P149. So it's Thursday 1 to 2 p.m. Yes, I hope to see you there. If you have any questions and you want to ask outside the past sessions, just go to the discussions folder on your interviews, and there's a past folder there. So that's how you contact me. All right, thanks.
Okay. It just seemed a little bit loud. All right. So far, we've got up to the stage, we've looked at some first order ODEs, a few methods, not all of the methods, and then there are still a lot of others that we don't have methods for, but we could get approximate solutions using computers. We moved on to second order ODEs, and we've looked at constant coefficient ODEs, homogeneous, and we found that you use the lambda method to get two solutions, generally exponential type solutions. There are three cases with the lambda method that you have to apply properly, but we can find the solution to the homogeneous second order linear constant coefficient ordinary differential equation. And now you see how far you've come. You know what all of those words mean. All of that has an understanding for you, doesn't it? So that's good. We also looked at the non-homogeneous case, and we found that we can use the method of undetermined coefficients, which, remember, only applies to that linear constant coefficient, second order case, must be constant coefficient. We also looked at a slightly more technical method called variation of parameters, and that's applicable to a broader case of differential equations. It still has to be linear, and but doesn't have to be constant coefficient. So it could be a differential equation with variable coefficients, and we're going to have a look at one particular case at the moment. So up to now, we've looked at, say, y double dashed plus ay dashed plus by equals some right-hand side function of x. That's the linear second-order constant coefficient case. And now we're going to allow these coefficients to vary as well with x, to be functions of x. But not generally. We're just going to look at one particular type called an Euler-Cauchy equation. Now, everybody say Euler-Cauchy. Euler-Cauchy, good, not Euler-Cauchy or something else. Euler-Cauchy, right, equation has this general form. Now, it looks a little bit technical there, but you see at this stage that whatever n is, if n was 10, then you'd have a power of x to the 10 multiplying and some other number. And then you'd work your way down, so from 10 you'd go to 9, because 10 minus 1 is 9, and that would be multiplied by an x to the power 9, all the way down to a first derivative multiplied by x to the power 1, and y by itself, which you could think of as a 0th derivative, and so that's multiplied by x to the 0, and x to the 0 is 1, almost always, except when x is 0, because 0 to the 0 is undefined, good. And if this is not identically 0, then this is the non-homogeneous case. But if it is equal to 0, then we'd have the homogeneous case. So, of course, we'll start off with the simplest second-order case. This is the Euler-Cauchy equation, homogeneous, and you see that you identify it as being Euler-Cauchy because the derivative matches the power of x for each term. Second derivative, x squared. First derivative, x to the 1. 0th derivative, x to the 0. And they can also be other constants times those things there. If there was a constant here, this says there could be a constant out the front, but in this case I've already divided through by that constant, so that the constant here is 1, and we have it like that. Now that's linear second order. It's not in standard linear form. Remember, standard linear form has to have the complete leading coefficient 1. We could put it in standard form by dividing through by the x squared, and we get this sort of thing, because you'd have an x divided by an x squared would be the 1 on x, and you'd have a b divided by the x squared would be a b on x squared, and the 0 divided by x squared would still be 0. So it would look like that, but that's not as easy to recognise as this. So that's the way that we generally work with Euler-Cauchy equations. But we do see that comparing this to this, we see the difference. Here we have a coefficient that isn't just a constant, it's a function of x. It's a special function of x. And here is another coefficient that's not a constant, it's another special function of x. So we're talking about second order, linear, non-constant coefficients. And there are lots of others. These could be any old functions, but this particular function is one that we can actually solve. So that's why we're looking at it. Well, remember when we came to look at this equation, second order, what did we do? Think back, and I know you'll have this in the top of your mind because you've been reading over your notes in the 6 or 7 hours that you spend on this class every week out of class. Good. You'll remember, of course, that a good mathematical strategy when you come across a new problem is to go back and ask yourself, and particularly if this was homogeneous, is there a simpler related problem that we can already solve? Well, if we go from second order to first order, and we went like that, if that was y double dashed plus by equals 0, then if you think about it, that's where we thought, well, exponentials solve that. That's really just exponential growth or decay if that was equal to 0. Exponentials solve that. So we'll chuck an exponential into this, equal to 0, and see what comes out. And remember that that's when you found the first, you put the e to the lambda x there, and you found the first derivative, you got an extra factor of lambda, and you found the second derivative, you got an extra factor of lambda, which gave you lambda squared. And that's where the quadratic equation, the lambda squared plus a lambda plus b, comes from. Okay, so that was the idea there. Let's use that same approach here. Well, is there a simpler related problem? Well, of course, if we looked at something like this, first order, and we divided through, well, suppose we came back to this equation, looked at the first order case, got rid of the a, divided through by a, then it would be first derivative plus some constant divided by x times y equal to 0. And that's what I've got here, except I've just called the constant a here. This a is the different a to this one. But that's the simpler version, first order, of this sort of problem. You see that the power of the x still matches the derivative. First power, first derivative, 0th power, 0th derivative. And can we solve that? Well, yes, of course. If we just take x bigger than 0, we're just looking for a suggested type solution. Then one way of thinking about this would be as linear, first order linear. And so that would be the p function, that would be the r function. We would find the mu function in this way, go through this process, take the a up as a power, e and the log would cancel, leave you with x to the a. Plug it into, so that's the step of finding the mu. Plug it into the formula. Remember the formula here was mu y equals integral of mu r dx, so that's what's gone on there, and you end up with something like this. Now, as an exercise, solve using separation of variables. That's probably the way that you would actually, if you ever got that equation, you would think first about doing that. But it's another way. Solve it using exponential. Solve it using separation of variables, and see that you get the same sort of answer. Okay. Now, in fact, another way to think about it. Look at this equation. If I wrote it like this, okay. If I wrote it like this, and remember back up here, when we looked at the simpler equation here, we ended up with something like dy dx equals, well, if we just thought of y dashed plus by equals 0, then we could solve that separating variables, that sort of thing. But another way to think about it is what function, when I differentiate it, gives me the same function except times by constant. And the sort of function that comes to mind there is the exponential function. When you differentiate an exponential function, you get the same exponential function except it's times by constant, the derivative of the power of the exponential. And another way to think about this thing here, we've already got the clue that it's powers of x, but we can see that from here. What function, when you differentiate it, gives you the same function except with the power dropped by 1? You see, dividing by x is dropping the power by 1. And we know that when you differentiate a polynomial, an x to some power, what do? You bring the power down, and then what do you do to the power up there? You subtract 1, don't you? Derivative of x cubed is 3x squared. You know, so x cubed divided by x is x squared. So if we, in fact, even if we looked at just that equation and thought about it for long enough without either solving it this way or solving it using separation of variables, we could get an idea of what sort of functions would make that true. Because this is saying which function, when I differentiate it, gives me the same function except the power of x has been dropped by 1 because you've divided by an x here. Okay, and that's polynomials. Now forget about the minus sign there. We don't care about that. I could have made it negative a up here and that would have come out as a positive a here. The clue that we're getting from this is that the sort of function that solves this equation, so the sort of function that might solve this equation are powers of x. Just like we had the clue from up here, the sort of function that did solve this was exponentials, so the sort of function that might solve this would be exponentials as well, or might be exponentials as well. So let's have a look just at, we're guessing here. We've used this approach to give us a clue of powers of x. We're guessing still, but let's see if it works. Let's try. So to substitute into here, what will I need? Well, I'll have that's x to the m. I'll need a derivative, and I'll need a second derivative. So the derivative is bring the power of m down, subtract 1 from the power. And then to get the second derivative, I'll do the same thing again. I'll multiply by the power. So I've already got an m there. There's the multiplying by the power. Subtract 1 off the power again. m minus 1 minus another 1 is m minus 2. All right, so we substitute. We can see that we have the x squared. There's the derivative, the second derivative. There's the ax. There's the first derivative. There's the b. And there's y. Okay, so we've just substituted in there. Now, we get actually to see why Euler-Cauchy equations can be solved. Because actually taking a first derivative subtracts 1 from the power, but multiplying by the single factor of x brings the power back to x to the m. And taking a second derivative subtracts 2 from the power, but multiplying by the x squared brings it back to a power of x to the m. So we end up with an x to the m there, same thing there, same thing there. So there's a common factor all the way through. For our purposes at this stage, we're just assuming x is bigger than 0, so that would mean that I could cancel that because I know it's not 0. By cancelling, I mean I'm dividing both sides by it, which leaves me with this equation. Okay? So what does that equation tell me? It tells me that if I can solve it, and what sort of equation is it? Well, if I expanded it out, I would get an m squared, and I'd have am minus another m, so that's a minus 1m, plus b equals 0. So we can see it's a quadratic equation. How many solutions do I generally get for a quadratic equation? 2, which would give me generally 2 values of m. And that would then give me x to the something and x to the something else, 1 for each value of m. That would give me 2 solutions. Okay? This is a linear equation, which means that for any solution, a constant times any solution is also a solution. So a constant times the first power of x, and a constant, another constant, times the second power of x will also be a solution. So that's telling me that if I've got x to the m1, that's one solution. And if I have x to the m2, m1 and m2 are the solutions to this, that's another solution. Because it's linear, I know that a constant times either of those, that will also always be a solution, and that will also be a solution. And because it's linear, the sum of any 2 solutions is also a solution. And if I call that solution y, then what could I call that for this differential equation? What's its special name? We can look at it. We see that it is the... I don't know. We see that it's the... What do we call it when it's got the 2 arbitrary constants for a second-order differential equation? It's the general solution. All right? So you see that from solving this quadratic equation, we identified any 2 solutions and we built them together to form the general solution. Okay? Just like we do for the e to the lambdas. Okay, but things aren't quite that straightforward because we know that, in fact, the sorts of the solutions that we can get are either a pair of real distinct solutions where the first one's not equal to the second one, or a pair of real solutions where the first one is the second one, or a pair of complex conjugate solutions. Okay, complex conjugate, remember, it means same real part and imaginary part, except one's positive and one's negative. And that comes from the quadratic formula, because the quadratic formula has the plus or minus square root bit in it. Okay? And we can handle each of those in much the same way as we handled the other ones. Let me go through here. You see that this was, if m1 and m2 are different, then these 2 functions aren't linearly dependent, which means one's just not a constant times the other. And here is the solution, except the only difference between what I wrote here and what I wrote up here is these absolute value signs. When we did this, I assumed that x was bigger than 0. You see back on the previous page we said assuming x is bigger than 0. It turns out, and I won't go through the derivation of it, but it turns out that for x less than 0, it ends up as being the absolute value. Okay? So if the question says x bigger than 0, you don't need to bother about the absolute values. But if the question doesn't tell you well, if the question says, basically shows you that x could be positive or negative, then you do need the absolute values in there, particularly if you have things like square root, half powers, that sort of thing. Okay, so that's the first form. I'll go through and I'll show you the forms of these solutions straight off now that we see that there are going to be three different forms. When we end up with two solutions that are the same, this is the case 2, the form looks like this. Now this is the same power, it's the same power here except we have a second function multiplied by a log function. And the case 3, where we end up with a y equals alpha plus or minus I beta, then the alpha goes out the front here and we get this cos beta log x and sine of beta log x. Okay? Now, all of that looks, and probably sounds and looks when you first see it, fairly complicated. But why I wanted to show you those three just quickly is to show you this. If we start with y double dashed plus a y dashed plus by equals 0, that's the constant coefficient case. And we would write down lambda squared plus a lambda plus b equals 0. And in the first case, if we get two different values of lambda, the solution is constant e to the lambda 1x plus another constant e to the lambda 2x. If we only end up with one value of lambda, then it's c1 e to that value of lambda, but then I have to have the same exponential function, except just doing this wouldn't be good enough, because that would just really be one constant times e to lambda. I need a linearly independent function, and the linearly independent function that always turns out to be is this x e to the lambda x function. And in case 3, I end up with e to the lambda x outside of e to the alpha x, that is, this is for y equals alpha plus or minus I beta, cos beta x plus b sine beta x. All right? So that's the constant coefficient case that we've seen, the lambda method. What we're looking at now is the Euler-Cauchy. So that's constant coefficient, and this is Euler-Cauchy. And we now have the x squared y double dashed plus ax y dashed plus by equals 0. And instead of writing the lambda equation down, we write this equation down. m minus 1 plus am plus b equals 0. Now you see there's a strong resemblance. This was actually quite easy. We didn't have to go through that process of substituting the e to lambdas in to get this every time. We just remembered it because the second derivative went to a lambda squared, first derivative went to a lambda, 0th derivative went to a lambda to the 0. Okay? Similar thing happens over here. We identify that it's Euler-Cauchy because the powers of x match the derivative in each case. And we still, for the first term, this is almost m squared. It's not quite m times m, it's m times m minus 1. So that's the only real difference between these two things. It's still two factors of lambda for the second derivative and two factors of m for the second derivative in the Euler-Cauchy equation. But in this case, the factors aren't quite the same. Instead of m times m, it's simply m times m minus 1. All right? Now, I did write down the other form. This was the other form that you could learn it in. But I'm going to suggest that you don't learn it this way. It looks easy. All you do is instead of having the a there, you put an a minus 1 for the Euler-Cauchy. So that looks easy. But I'll tell you why I prefer you to learn it like this. Firstly, you see the connection. It's two factors of lambda compared to two factors of m. But also, we're going to go to third order constant coefficients. And can you imagine what we'd have out here if it's a third order? A lambda cubed, okay? And this works much more easily as well. If I had an x cubed y triple dashed out here, can you imagine what I'm going to have out here? M times m minus 1 times m minus 2, all right? And that's much easier to remember than expanding all of that out, and you get horrible coefficients and things for the m cubed type thing in that case. So this is the better way to learn it because it generalises more easily. All right. Now, what are the three forms of solution? Well, the general solution to the homogeneous equation we've seen. I won't write the absolute values in, but you understand that the absolute values are there if needed. And I write it this way. Okay, now if you stare at those long enough, you start to see some similarities. Okay, you start to see some similarities, especially if I write these like this. C1 e to the x to the power lambda 1 plus C2 e to the x to the power lambda 2. You know in this case you multiply powers. When you take one power to another power you multiply, so that's where that comes from. This is C1 e to the x to the lambda plus C2 x e to the x to the lambda, and this is e to the x to the alpha outside of a cos beta x plus b sine beta x. Now why did I write it like that? Well, what I'm trying to help you to understand here is that even though these did originally look a little complicated with all the logs and stuff in there, there's not a lot more to remember for these once you know these three. And you do know these three because you've spent all of that time over the last few weeks learning them and using them. Okay? Why are they similar? Well, they're similar. Look at this. This is something to a power, and I've shown you that this is something to a power. Something to a power, the same, well, it was x to the power, the same thing to the power, e to the x to a power, e to the x to a power. So it looks like, to get from this to this, e to the x has gone to x. So if I just change that to x, I'd get x to a power, and there I have x to a power. X to a power, there's the x to the power. Now, if e to the x went to x, how do I get from e to the x to x? What do? I take logs, don't I? If I take log of e to the x, that just brings me to x. So e to the x going to x is the same as x going to log x. So let's look at this second case. E to the x, I've got something to a power. You see I've ended up with something to a power. There is the something to a power, there something to the power, but this x has gone to log x. All right? Here I have something to a power, so the e to the x has just gone to x, and the x's in here have gone to log x. Okay? So you see the form of each of these is really the same, except we've used this transformation, e to the x goes to x, and x goes to log x to get from one to the other. Now, that's a good way to remember it. They're the same sort of forms. It's two parts that are different, two parts that are the same except for multiplied by a product, and then there's something outside of a cos and a sine term. The forms are very similar for each of those three cases. Now, mathematically, when that happens, that doesn't happen by accident. All right? And the real underlying reason as to why this happens is that if you start with an Euler-Cauchy equation, you can actually use a substitution. Just like you do a substitution in an integral, you can actually use a substitution here. And if the substitution is x goes to e to the x, then that actually will transform any Euler-Cauchy equation into a constant coefficient equation. All right? So that's the real underlying reason, is that an Euler-Cauchy equation can be transformed into a constant coefficient equation. All right. So, but for our purposes, once we know these forms are actually very easy to learn again because they're not all that different. Good. Now that we've got that far, let's go back to case 1 and now look at some examples. So if we have this, we write down the auxiliary equation. For Euler-Cauchy equations, it's called the auxiliary equation. For the constant coefficient, we call it the characteristic equation. They're just names we give to them. So let's look at this. Here's the example. I write down, you can see it here, two factors. We first of all check that it's Euler-Cauchy. Powers of x match the derivative in each case. And then for the second derivative term, I write down two factors of m. For the first derivative, I write down one factor of m times the 2. And for the 0th derivative, I write down 0 factors of m. It's a factor of m to the 0. So there's the minus 6. Expand that out, and you see that effectively all that does is subtract 1 off the coefficient here, so we go from 2 to 1. We notice that we can factor that, and we get two values, 2 and minus 3. Which case is it? Well, we know this is case 1 because that's the example we're doing, but it's case 1 because we've ended up with two real and different answers. And once we see that, we can throw it straight in as powers. So there we have it there. Why haven't I put the absolute values in? Because the question told me that I could take x bigger than 0. If that wasn't there, I would need the absolute values, and then I'd take one of the absolute values away, because anything squared is positive anyway. So you wouldn't need the absolute value in that case. You would still need it in this case. Okay? So the second case, as we've seen, can be written like this. So let's look at this example. Is it Euler-Cauchy? Well, I can see that the second derivative term matches, it looks like Euler-Cauchy because the power of x matches the derivative. And certainly here for the 0th derivative, but what about the middle term? How do I know that that's going to match? Well, I could write this as 4x squared d2y dx squared plus dy dx plus y equals 0 with a 0 in there. That's the same thing, but that wouldn't be Euler-Cauchy. Alternatively, if I put an x in there, that would be Euler-Cauchy. Am I allowed to do that? Because 0 times anything is 0. Okay, so I can put whatever I like as that second term there, and if I choose to make the whole thing Euler-Cauchy, then that just means that I've got a 0 coefficient there. All right? So you see that's where we're from here, and the same thing also happens, remember, for the lambda method. We don't have to, even though the standard form of the Euler-Cauchy equation doesn't have a constant, well, it has a constant 1 out here. Here it has 4. What technically we should do is divide through by 4, but then this equation would have been divided through by 4, and I could have multiplied back by 4 anyway, because I've got a 0 on the right-hand side. So I can just go straight from there with the coefficient there of 4, a 0 for the middle derivative, and a 1 for the last term. That turns out to be this, which is a perfect square, for which I get one answer. Because I've got two answers, but they're the same, it's the second case, and the second case says, take the first solution, we'll take the power, and I've written it in this factored form, so there it is, with the power of x out to the half. Now, I'm not told anything about x, so I do need the absolute values there, especially as it's a half, and especially as I'm taking logs. So that's why the absolute values are needed there. Good. Any questions? Good. Easy, straightforward, sort of. And the third case is when the quadratic equation gives you complex conjugate roots. So here we have them. The form here is an example. In this case, we're told to take x as positive. That just now in our mind ticks off that we won't need the absolute values in the solution. We write straight away for the second order term, 2 factors of m times the constant. For the first order term, 1 factor of m times the constant. For the last term, it's just the 1, equal to 0, which gives me then when I factor it, well, then when I expand it, I find that I try the cross method and I try whatever other method I want. I can't factor it, so I go to the quadratic equation. Second term is the minus b plus or minus root b squared minus 4ac all over 2a. Gives me, when I do the calculation, I get this. Now, students can get down to here, but they do this wrong. So check that you can get the simple arithmetic correct in doing that. So what does that mean? That means that alpha is minus a half, and beta, which remember is the thing without the plus or minus and without the I, is also a half. And so looking up here, I'm going to put a half there, and I'm going to put a half there and a half there. All right? So, sorry, I'm going to put a minus a half there and a plus half there and a plus half there. So that's what we have as the solution. And this last bit is just that comment that I made about the transformation. Any questions? Case 1, case 2, case 3. Good. Well, you can obviously all do these yourself, so there you go. Have a go at that one. What does this mean for us? It means we don't have to bother about the absolute values in the answer. Okay, so step 1, write the auxiliary equation down, the M equation. Write it down for that example. Well, actually, step 0, if you like, is it Euler-Cauchy? Do the powers of x match the derivative? Do they here? Do they in the derivative term? What's the constant times going to be there? 0. Remember that we can add, what's hidden in there is really a 0 x y dashed, and then the last term, yes. So yes, we can make it Euler-Cauchy if we have this middle term done properly. So write down the M equation for that. So the M equation will be m times m minus 1 plus 0m minus 2. What you got? Good. Expand that out. M squared minus m minus 2. Can you factor that? Try the cross method. See if you can do it yourself. Factor m squared minus m minus 2 equal to 0. And hopefully you've got answers of minus 1 and 2. So that's where we're up to there. But the important thing is not that you look at this on the screen and you say, yes, I could have done that. The important thing is that you've actually done it yourself. All right, so have a go, write down, decide which case it is, and write down the general solution. Is it case 1, 2, or 3? Case 1, which would make sense, it's the first exercise, but yes, it's case 1 because you have 2 real different answers. So, have you written the solution down? Good. And there it is. Okay, any questions? If we hadn't been told this, then I would have needed absolute values around this x, but I wouldn't have needed absolute values around this x, because anything squared is positive anyway. Go, try it, do it. Yeah. Zeroth step, is it Euler-Cauchy? Yes, powers of x match the derivative. Good, so this is the method that we can use. First step, write the auxiliary equation down. 2 factors for the second derivative term, 1 factor for the derivative term, no factors for the y term, zeroth derivative term. Expand it out a bit, which is essentially just subtracting 1 off the middle term, and then decide whether you can factor it using the cross method or some other way, or whether you need the quadratic formula. So that's where you're up to. Does it factor? No. So try the quadratic formula. Minus b plus or minus root b squared minus 4ac all over 2a. All right, now look at your answer. Hopefully you've ended up with this. And we need to decide, is it case 1, case 2 or case 3? What's case 1, case 2, case 3? Well, it's not 2 because we've got 2 different answers. We've got 2 plus root 7 and 2 minus root 7. So it's either 1 or 3. Which is it? Good. Okay. Why is it 1? Because there aren't any i's timesing this second term, are there? Root 7 is a number between 2 and 3. 2 squared is 4, 3 squared is 9, so the square root of 7 is a number between 2 and 3. 2 plus a number between 2 and 3 is a number between 4 and 5. 2 minus a number between 2 and 3 is a number between 0 and minus 1. Okay, so they're just 2 different numbers, even though they've got this plus or minus business between them. And just because they're 2 different numbers, that means that it's still case 1. And we just put those in as powers. This is a positive power, this is actually a negative power. Good. Next exercise. Euler-Cauchy, looking at it, yes. So we write the M equation down. and expanding it out, and hopefully you've been able to see that it's a perfect square. Except it's not. Sorry. There are two ways to look at this. You see that this is the difference of two squares. You remember your formula that says x squared minus y squared is x minus y, x plus y. So this is something squared. The thing that's squared here is 2m, and the thing that's squared here is 1. So we can think of it the first thing minus the second thing, which is what we have there, and the first thing plus the second thing. In fact, probably a better way to solve this would be to just say that then 4m squared equals 1, which means that 2m equals, take the square root, what's the square root of 1? Plus or minus, you must remember the plus or minus 1, which means that m is plus or minus a half. So either way, you could either recognise it as the difference of two squares or solve it in that way. You end up with two values. Are they the same or are they different values? Plus or minus a half. Is plus half the same or different to minus a half? Different. So which case is this? Case 1. Any questions? Okay, so each of those were case 1, but you just throw anything else in for, there we are, for case 2 and case 3. So we'll have a look now. So, Euler-Cauchy, yes. Powers of x match the derivatives. Write the characteristic equation down. That's what we get. Think about how you'd factor that. And just thinking about this, for your class tests and for your final exams, remember that while you may be able to pass if you know the work. You definitely need the work to pass, but you also need to be able to do this sort of thing quickly enough. You need to be so confident with it that you can look at that and you can either recognise it as a perfect square or factor it very, very quickly, because class tests and final exams and things are timed so that not only do you need to know the work, you need to be able to do the work competently. Okay, not just sitting there for 5 minutes thinking about how to factor this. You might know everything how to do, but if you take 5 minutes to do this, then that's 5 minutes that you don't have to be getting other marks through the test. So once again, I'm just emphasising the point that you need your algebra, calculus, derivative, integral skills. Okay, not just thinking I did them last year, but or last semester, but you need to have them so that you can do them. So that you can look at this and you can factor it straight off and write this down and go from there to there very, very quickly and accurately. So we end up with a -3. We actually have two values. It's -3 and -3. It's just the two values are the same. Which case is this? Second case. Can you write the form down without going back and looking at it? Okay, well, go back and look at it and write it down. Now, if you went back and looked at it, hopefully you were able to write that down. You could factor it. You could take the factor of the x to the minus 3 outside, but you don't have to. And once again, there are no absolute values here because we have been told that x is positive. But if we hadn't been told that, we would need absolute values in each of those places. There we go. Last exercise. I wonder if you can guess what case this is going to be. Have a go at it. Euler Cauchy? Yes. So then we write down the two factors of m, one factor of m, no factors of m. Expand it out. Solve the quadratic equation accurately and quickly. Now, once you've solved that, then you need to identify the alpha and the beta. Once you've solved that, can you identify the alpha and the beta? Okay, well, we're obviously going to get from this m squared equals minus 1, which means m is what? Plus or minus. When we've got that squared, we do this, and plus or minus the square root of minus 1, but the name that we give the square root of minus 1 is I. All right. Now, what are the values of alpha and beta out of that? Alpha is, beta is. Good, because we say that this is the same as 0 plus or minus 1i, and that's where we get the alpha and the beta. All right, you plug that into the third form of the solution. And can you simplify that? Yes, you can. So there we have it, which simplifies out to be, that's just becomes a 1, well, and that's what we have on the end there. So that is the general solution in explicit form. All of these always for linear equations come out to be explicit form. Well, it can't be 0 because we've got the log here. So, yeah, it won't be 0. No, I know that I can see that it can't be 0 because I'm using the log function. I'm using the log function. Yep. So you wouldn't need to write. Yeah. So I understand what you're saying. If I wasn't cancelling there, I was just saying that x to the 0 equals 1, as long as x isn't 0. So I'm not dividing through both sides of anything there. I'm just saying that's equal to 1. And I know that x isn't 0 anyway because I'm using log function there anyway. If I hadn't been told that all of these have x bigger than 0, if I hadn't been told that, then tentatively x could be 0. But as soon as you've got case 2 or 3, case 2 involves a log, case 3 involves a log. As soon as that happens, x can't be 0 anyway. And x won't be 0 if any of these values in case 1 are negative. Okay? So x equal to 0 sometimes will be available even if you're not told, but generally x isn't equal to 0 in these anyway, which is why I can quite happily take x to the 0 here as 1, because I know that x isn't going to be 0 because I can't use it there anyway. Okay, well we've looked at constant coefficient, homogeneous, that's the lambda method. For non-homogeneous, we use either the undetermined coefficients table or variation of parameters. And now we have one example of non-constant coefficient, second order, linear, and we won't be able to use the table of undetermined coefficients because that only works for constant coefficient. But if we want to look at a non-homogeneous Euler-Cauchy equation, we will need to use variation of parameters. And we will do that in about 5 minutes. So you can have a little break now. Okay. Let's look at this example then. So the first question is it Euler Cauchy? Yes or no? Obviously, because that's what we're doing, but yes, we have checked the power of the x matches the derivative. So yes, it's Euler Cauchy. And now there are two reasons that we can't use the table of undetermined coefficients. Okay, remember that table given the right-hand side? The first reason is that you can only use that for constant coefficient case, and the Euler Cauchy is not constant coefficient. So that's the first thing. And the second thing is, in this case, the right-hand side isn't even one of the ones in the table anyway. Okay? But the main reason is you can only use the table of undetermined coefficients with the non-homogeneous constant coefficient case. That's the one you use the lambda method to solve the homogeneous case. Okay. All right. So what type of equation? Euler Cauchy. What does the equation tell us about x? It's got to be positive. So the equation itself tells us that x is positive. Why does it do that? Because it's got the log in there. You can only take log of positive numbers. And why is that helpful for an Euler Cauchy equation? It then tells us whether we need the absolute values complication in the answer. Okay? And in this case, we won't. All right. So, what are the steps now to solve using the technique of variation of parameters? First step was to solve the homogeneous case. Okay? Second step was then to go through those steps of finding the Wronskian, identifying the R function, figuring out mu and nu, plugging that all together to get a particular solution, and then adding the homogeneous to the particular to get the final general solution to the non-homogeneous case. So that's what we're going to do. Step one, find the homogeneous case. Now, I've glossed over this just for a moment, but I'll come back to this. But just for the homogeneous case, we can think of it in this form. How do we solve that? 2 factors of m, 1 factor of m, no factors of m, expands out, perfect square. This is the case 2. Okay? X to the power 1 and x to the power 1 log x. So that is, you can check that, case 2. Second step was to identify y1 and y2, those parts of the homogeneous equation. So that first part is what we're going to call y1, and the second part is what we're going to call y2. And then we need to find the Wronskian. The Wronskian, remember, is y1 and y2 written across, and its derivatives underneath. The derivative of x is 1, but this is a product, so we need to use product rule. The second thing times the derivative of the first is log x, and the first thing times the derivative of the second, well, the derivative of log is 1 over x, so you have x times 1 over x is 1. All right? And then we do the determinant by multiplying the x by all of this term and subtracting off this product, which is what we end up with here. And you see that, in fact, subtracting off this product just leaves me with x. Now, all of this you have in front of you, and you will go away, and in the time that you owe me outside of class, you will redo this example by yourself without looking at the answers. And if you have to look at the answers, then you will redo it again until you can do it without looking at the answers. Okay, so what's the next stage? The next stage is to build the particular solution out of all of the bits and pieces. One way to do it is in this form, which, remember, this is mu y1 plus mu y2, and that is the formula for mu, and that's the formula for nu, because mu was the integral of minus y2r over w dx, and nu was the integral of y1r over w dx. I actually prefer to do each of these separately. So figure out mu in a series of lines by itself. Over here, figure out nu in a series of lines by itself, and then put them together like this at the end. But this is just a different format way of writing it out. Okay, and this is the y1, and that's the y2. So you see you have mu y1 times nu y2, which is what we have there. Okay. Also, another check to make sure that you've written this out correctly is that the rest, once you've written down the first part, the rest of the integral is the same. Okay, that's the minus y2, and that's the y1. But the rest of the integral is the same. You see, it's r over w in both cases. So the rest of the integral there is the same. Now, this is where your algebra and your integral calculus skills must be good. You must be able to do the correct cancellations here, you know, without really thinking about it too hard. Of course, they often get done without thinking about it too hard, but the point is you have to do them correctly, be able to do them correctly without thinking about them too hard. So these x's cancel. We're left with a log x all squared, and remember that log x all squared is not the same as log of x squared. Okay? Because log of x squared, we know we can move the 2 down the front, and something squared isn't always equal to 2 times something. Okay? So these two things are not equal. So this is log of x all squared. In this case, the x's cancel, and I'm just left with log x over x. Now, so that's the algebra part. It wasn't too hard, but you have to be able to do it accurately and correctly. Now we look at this and we say, well, how do we do those integrals? I have something over something else, so the first thing I think about is it a log rule? Can I see the derivative of the thing in the bottom on the top? Remember, the integral of f dashed of x over f of x is log of absolute value of the thing in the bottom, thing in the denominator. Okay? Now, so we look at this and we say, is that of that form? It's something over something. Well, no, the derivative of x is 1, and I don't have a 1 on the top. Okay? So the next thing when we see something over something else is, well, is it one of those inverse tan or inverse sine or inverse cos ones? And you go and you look at the table and you know the forms of these in your head, and no, it's not one of those. And so the third thing you think of is it a substitution? What question do I ask myself for a substitution? The question I ask myself is there a function there whose derivative I can see multiplying? Okay, well, the function that stands out there is a log x. What's the derivative of log x? 1 over x. So can I see a 1 over x there somewhere? And in fact, yes, I can. It's a 1 over x and a 1 over x. All right? So if I let u equal to log x, then du is 1 on x dx. So what does this first integral become? This first integral becomes the integral of minus u squared, and then the 1 on x, remember there's a sort of a hidden 1 there, it's really times by 1, so there's a 1 on x dx, is the same as du. That's what this says here. And the second integral, this becomes the integral of u du. There's the u, and the rest of that is du. So what's the integral of minus u squared with respect to u? Add 1 to the power, divide by the new power, so that's a u cubed on 3. So, but u was log, so this will turn out to be log cubed over 3. And what's the integral of u? U squared on 2, this was minus u cubed on 3. But u is log, and so there is the log squared on 2. Now you might take a few extra lines and do this, do these integrals slightly differently, but that's how we get from there to there. In each case, is using those substitutions. Now, I also haven't put the plus c. Why didn't I put the plus c? Well, we spoke about this last week. We don't put the plus c here because it actually comes out later on when I build the final solution. Those constants that are part of the homogeneous actually are where we get these plus c's coming back into the solution. Okay, so that's what we have there. We can expand all of that out. There's an x log cubed, there's a x with another log cubed, and then we have to be able to do, look, I look at that and I say, well, actually that is exactly the same as that. So I have a half of something minus a third of something. Well, a half is 3/6 and a third is 2/6, so 3/6 minus 2/6 is 1/6. Okay, so you have to be able to do that arithmetic correctly to be able to say, what's a half minus a third? A half minus a third is a sixth. And that's what we have there. And the third step then is to put that together with the homogeneous solution to build the general solution. Any questions? Okay, I had a couple of questions during the break as to what sort of formulas you'll be given in the class test and the final test and all of that sort of thing. And just to mention to everybody, there are sample class tests and final tests in the on the View site. The sorts of formulae that you get will be on the also there. The class test, have a look at past class tests. Obviously, the formula sheet, we haven't covered everything that is covered on the formula sheet, so you might only get the first part of the formula sheet that's relevant. All right, but these sorts of formulae aren't given. Okay, you are given a version of these formulae, but we haven't quite got up to that stage to explain that version to you yet. Question? The two class tests are 15% each. Yep. Okay. Here we go. We note this. We say, first question, Euler-Cauchy, yes or no? Good. Homogeneous or non-homogeneous? Non-homogeneous. Do I use the table of undetermined coefficients? No, I never, ever, ever even think about using the table of undetermined coefficients when I have an Euler-Cauchy. Even though I could use this if this was constant coefficient, I could use the table of undetermined coefficients. Because it's Euler-Cauchy, because it's not constant coefficient, I must not use undetermined coefficients. I must use variation of parameters. That's because it's not constant coefficient, not because of the right-hand side. Okay, there you go. First step, solve the homogeneous case. Go. Do it. So, two factors, so you'll have an m times m minus 1 plus a 6m plus a 4, which will leave you with an m squared plus a 5m plus a 4. Can you factor that straight away? What numbers multiply to give 4 and add to give 5? 4 and 1. So m plus 4 times m plus 1 equals 0. That means that m is minus 4 or minus 1. Good, we've done that. You can write it's the first case because you have two different numbers, and there's the general solution to the homogeneous case. So you see the steps? straight off. And why didn't we have the absolute values there? Because we were told that x was positive. Second step. Okay, this is the variation of parameters part. Oh, and I did say that just a comment. I did say that I would come back and mention this line, but then I didn't. Okay, notice here the value that I'm using for R. Look very carefully at that R. That's what the R is there. Okay? But look here, this says x log x. Why isn't that R? Because when we use variation of parameters, we do have to have the equation in its standard form. And standard form means I must have divided through by the x squared, which means instead of x log x, I've had x log x divided by the x squared, which is where that came from. Okay? Variation of parameters says the R value that you use is when you have the equation in standard form. Standard form means the leading coefficient is 1. Okay? So now that I did come back and mention that to you eventually, what will the R function be here? Okay, it will be, yes, I hear what you're saying, the x squared minus x divided by the x squared, because I have to put it into standard form. And doing the division, x squared into x squared is 1, and x squared into x is 1 on x. So that's what this line down here says, basically. You have it in standard form, so there is the correct value of R. The correct value of R is not x squared minus x. Okay. So the next step will be to identify, which order have I done this? Yep. Identify the y1 and the y2, that's where they come from. There they are. Okay, so you calculate the Wronskian. Write the Wronskian down and calculate it. The Wronskian involves the determinant. You write the y1 and the y2 across the top, and you write its derivatives underneath. And once again, you need to be able to do the derivatives of these things accurately and quickly. Okay. Derivative of x to the minus 4 is bring the power down, so that's the minus 4. And this is where students make a mistake. Minus 4 minus 1 is not minus 3. Minus 4 minus 1 is minus 5. Okay, just like minus 1 is minus 2. So there is the derivatives, and check that you can get that answer when you expand it out. And remember, when you multiply these in the determinant, it's going to be a minus minus. And then a minus minus is a plus when you do the determinant here. Okay, next step. We'll do it this way, I think, even though the notes aren't quite like this. No, okay, we'll do it the way the notes are. The next step will be to write down y equals the particular solution, sorry, equals now. How do we build this up? Well, we have the mu function there, and we have the nu function there, and we have y1 in there, and we have y2 in there. Okay? The mu function involves an integral, and so does the nu function. Can you fill those bits in? Have a look and see if you can fill those bits in. No, it won't in the end, for two reasons. Because they would have been switched here, and then you would have had a negative sign. And once, because there's a negative there and a not there, the negatives would have just worked themselves out in the way. So yes, if you'd called y1 x to the minus 1 and y2 the other way around, the working would have been very similar, except there'd been a few different negative signs around the place, and at the end it would have cancelled themselves out. All right, well, hopefully you've been able to fill both of those in. Remember, do the check in the integrals. The second part of the integral is the same in both integrals. Just check that you've got that. And so you should have ended up with something like that. There's the minus y1 and y2. There's the y1. There's the r over w. Is the same in both integrals. There's the y1. There's the y2. Okay, so that all matches up. That's what you're building. Now, once you've written that down, can you simplify those integrals using your powers of x and what you know about negative powers and that sort of thing? It's simple, but you lose marks if you can't do it correctly. So the way I would think about it would be the minus power means a 1 over. So if I'm dividing by a fraction, what does that mean I'm really multiplying by? You turn it upside down. So if this is a 1 over, dividing by x to the minus 6 means I'm really multiplying by x to the 6th. And so I could do a sort of an x to the 6th multiplication all the way through there. Would mean that x to the 6 times x to the minus 1 is x to the 5, and then x to the 5 times 1 is an x to the 5, and divided by another x is an x to the 4. So this whole thing will end up as x to the 5 minus x to the 4 with a minus and over 3. So that's what we have there. Okay? And similarly here, this really means multiplying by x to the 6. X to the 6 times x to the minus 4 is x squared, so I'll end up with an x squared times x to the power 1, which is what we have there. So which of those are easy integrals to do? But even though I say they're easy, you have to be able to do them quickly and accurately. That's what we end up with. And now, can you, once you've got to that stage, remember we don't need the plus c's just now, can you expand that out and simplify? Do the algebra. And with a little bit of work, if you haven't quite got there, check that that's the answer that you got or can get or will get when you try this again at home. Third step, what's the third step? To find the general solution, and I do that by what? Adding the two bits together. So third step, the homogeneous plus that particular solution we just found. Now, I make this point. Sometimes there are bits of the particular solution that are similar to here. So for instance, if this has ended up with a 3x to the minus 1, just imagine that there'd been a 3x to the minus 1, then a 3x plus a constant x to the minus 1 would still have been a constant. The constant would have been c2 plus 3, x to the minus 1. And so sometimes that would still be covered by this. So sometimes the answer can be simplified slightly if parts of this particular solution can be swallowed up, if you like, by the constants here in the general solution. So just give you a heads up there that can sometimes happen. Okay, second case, second example. This tells us we don't need the absolute values in the final answer. It is Euler-Cauchy. Yes, we see that. And it's non-homogeneous, so I'm going to have to use which method? Undetermined coefficients or variation of parameters? Have to use it. Variation of parameters doesn't work. Undetermined coefficients doesn't work for Euler-Cauchy. Okay, so first step, here we go. You can follow each of those steps. You see where they're coming from. So you see the two factors, the one factor, the zero factor, expanded out. Check that you can get those two values, and then we recognise it's case 1, so they go as powers. So that's solved the homogeneous case. The second step is to find the particular solution. We're going to use variation of parameters, so we need, out of the homogeneous, we need a y1 and a y2, so we'll pick those out from there. But we'll also need the correct right-hand side. What will the correct right-hand side be? The correct value of r to use in the formula for mu and nu. Good. Is it x cubed e to the x? No. We need to divide through first. And so that is the correct right-hand side, because we've divided by the x squared first, because variation of parameters assumes that you get the right-hand side from looking at the second order differential equation written in standard form, and standard form means leading coefficient 1. Okay, so that's where we get the y1 from, that's where we get the y2 from. Tell me what the Wronskian is. Calculate it for me. Right, I'll give you another 30 seconds. You should have been able to do it in 30 seconds. So you've written x and x squared, you've written the derivatives underneath, and then you've expanded the determinant and you've ended up with x squared. All right, so we're now going to write the particular solution in that form. Yep. If you choose it the other way round, then you get a negative, but the y2 and the y1s that you put in these formula will also be the other way round, and in the end, you'll get the same number, the same answer coming out at the end. But the reason we did it this way was just because you don't end up with a negative. Okay, can you fill these bits in for the particular solution? Put the formula, the bits and pieces you need there, the y1, the bits and pieces you need there, the y2. And what are the bits and pieces? It's the minus the y2, the right value of r over w, and it's the y1, the right value of r over the w. So fill that in and simplify those integrals. Now that second integral is going to be pretty easy. That's just the integral of e to the x. But this first integral is what? With a negative out the front, it's negative. And we do an integral like that. How? By parts. Okay? So we have to do that by parts. I'll show you the answer here. But you need to check that you can do that integral by parts. Remember, that's integral of u dv is uv minus integral of v du. And the way that you choose the u and the v, there's always a choice, whether it's the x is the u and the dv is the other thing, or the u is the e to the x and the dv is the x dx. But function equals function and differential equals differential, that's important. And then the other thing is that this integral needs to be easier than the integral you started with. So because there's a choice, you choose it the way round that gives you an easier integral. But we did do some examples of this in class already. I'm going to leave that with you to be able to check that you can get that answer for that integral by parts. And then after that, there's the particular solution, and you can add the two bits and pieces. This was step 2, this is step 3, the homogeneous plus the particular. Any questions? Yes, it's a bit of work involved in doing that, but really, it's all work that is, Eng Maths 1 and earlier stuff. The rest of it is, all of that's algebra. All that you've learnt really for this, for differential equations is recognise its Euler-Cauchy, know how to solve the Euler-Cauchy, which is just algebra, quadratic equation, and then secondly, recognise that it's non-homogeneous and know how to do the method of variation of parameters. And that involves bit of determinant, bit of integral stuff. Good. All done? Everybody there? Take a deep breath, roll, move your neck around a little bit, roll your shoulders, twinkle your fingers. Good. All right, and we now leave first order ODEs, second order ODEs. These are we've looked at a few situations where we can actually get complete general solutions. Now there are lots of other cases where you can't. Give me your attention. Shh, that's all the break you get. All right. What do we do in ordinary maths when we can't get, whenever we use pi to find the area of a circle? Do we ever get an exact answer if we write it out as decimals? No, because pi itself goes on forever and ever and ever. But we can certainly use the number we get out of our calculator, assuming we've calculated things to as accurate as we need. Now we can do a similar sort of thing with differential equations. Even if we don't have methods to solve them, we can go to computers to solve them, but we sort of need to understand what the computer's doing. And one thing that a computer sometimes does is to change the function into an approximation of the function. Now this approximation, like a decimal number for pi, goes on forever and ever and ever often. Sometimes it doesn't, like ordinary numbers, but often it goes on forever and ever and ever. But we can use that approximation, and as long as the answer that we get out, we use as many terms as we need to get the correct level of accuracy, then we are on the way to getting a handle on a solution to one of these things. And the approximation to the function that we use, one type of approximation is called a power series. And this is a little bit of work on power series. You've actually seen power series before. What if I had this? 1 plus a half plus a quarter plus an eighth plus a 16th plus ... Anybody recognise what sort of series we would call that? You've only ever done two types of series. One was called arithmetic and the other was called geometric. Which is this, arithmetic or geometric? Geometric. Okay? It's geometric because we have a term that keeps multiplying by itself. What's a half times a half? A quarter times another half. So this is 1, in fact it's 1 plus a half squared, plus a half cubed, plus etc. Now does anybody remember if that, tell me what that actually adds up to. If I go 1 half, 1 3/4, 1 7/8, 1 15/16 is where we're up to, what's that getting closer and closer to? 2, okay? It's getting closer and closer to 2. So the limiting, the infinite sum of this, we call 2. But we have a formula. Does anybody remember what the formula for the infinite sum is? For something or other? Does this ring a bell? A over 1 minus r. Yes, good. A is the first term, which in this case is 1. And r is what's called the common ratio. The common ratio in this case is a half. So what's 1 minus a half? A half. And what's 1 over a half? 2. Okay, good. So you've seen this. You've seen geometric series before. What if I make this a little more general? What if I say 1 plus 1 on x? 1 plus x. Plus x squared, plus x cubed, plus etc. Then we would say that that adds up to the same thing. What's the first term? 1 over 1 minus the common ratio. But we can now view this in a different way. This is a function. I could graph it. I could graph y equals 1 over 1 minus x. It's a hyperbola. It's going to have a problem when x is 1, so that's where the hyperbola will sort of go up to positive infinity and down to negative infinity when x is 1. Okay, but it's basically a hyperbola. So what this is actually saying is, if I have this function, I could approximate it by a certain number of terms of this series. If I went up to 100 terms, I could approximate it by that. There's something else about this that's a little bit funny though, because this sort of series doesn't always work. Obviously if it's a half it works, and if it's a quarter if it works. Even if it's minus a half it works. But what if it was 2? 1 plus 2 plus 4 plus 8 plus is? What does that add up to? It's a big number. What does that add up to if I keep adding an infinite number of things on? Infinity. But I can put a 2 in here, can't I? 1 minus 2 is minus 1. So 1 over minus, this has an answer for x is 2, but this doesn't have an answer for x is 2. So how are these two things equal? Well, if we go back to this, the other thing that you would have learnt about this is that this infinite sum formula only works for the value of r between minus 1 and 1. The absolute value of r less than 1 means r is between minus 1 and 1. And let me show you the reason why this works. If I were to graph this function, it actually looks like this. Okay, if I were to graph that function, it actually looks like that. Now, if I start at 0 and I use values between up to 1, I see that the reason that this is giving me a problem after 1 is because I've had to cross this break in the function. Okay? But will this also work, say, for -2? It doesn't work for 2 because I've sort of crossed over here, and this obviously is going to infinity. But what about for -2? If I thought of this for -2, this would be 1 minus 2 plus 4 minus 8. Does that ever get close and closer to any one number, like this gets closer and closer to 2 as you get up closer and closer? No, it's sort of jumping from a big negative to a bigger positive to a bigger negative, etc. So it doesn't, we call that convergence. This converges to the number 2, but if x is 2 or if x is -2, it doesn't converge. But looking at this graph, there aren't any problems down here. But see, what actually happens is, if you've got a problem on one side at 1, then the form of the function only works for the same distance on the other side of the function. So this approximation to this function doesn't work out here and doesn't work out here, but it does work in the middle. Okay? Now, if I had a two-dimensional circle, then its radius is the distance that I move from the centre out to points on the circle. And if I had a three-dimensional circle, which we also call a sphere, the radius is the distance that I move from the centre out to wherever I get points on the edge. Okay? So going out to there. So that was a two-dimensional circle and a three-dimensional circle. This is actually a one-dimensional circle. Okay? One-dimensional circle only has those 2 points. Can you tell me the radius of that one-dimensional circle? It's 1. It's the distance I move from the centre out to there. And what that's called is the radius of convergence of this approximation. Okay? So the radius of convergence is 1, and we give that a name, that's a capital R, called the radius of convergence, is 1 for this approximation to this function. Okay? Doesn't work out here, it doesn't work out here. And this also is an approximation. You can see the approximation is centred about the origin. Okay? So this is a power series about x equals 0. And you see that it matches up with what I'm talking about here, with all of these A0s and A1s just as 1. Okay? So that's where we're up to. With that little bit of background, here are some example power series that we have. It turns out, if you think about what a factorial number is, remember factorials, 3 factorial is 3 times 2 times 1. 10 factorial would be 10 times 9 times 8 times 7. The only other, so in fact, and 1 factorial would just be 1. So in fact, we could extend this a little bit. They extend the pattern coming back. And if we wanted to extend that pattern coming back even further, what would I have to write there? Okay, 0 factorial. And it turns out that a good value for 0 factorial is also 1. Okay, so we can use 0 to the 0 doesn't have a value. 0 factorial does have a value, 1. Okay. Similarly, you could see that that extension of the pattern also works back here for those power series. Okay. Now, a couple of things to mention. Where are these? Well, let's think about what's happening. Here, I said that if I made x too big, even if I made x 2, I get problems. All right? What about this? What if I made x 100? Well, as I start to get up to 100 to the power 10 and 100 to the power 20 further out here and 100 to the power 30, all right, then that's going to get pretty big sort of number. But if you think about actually then what it's being divided by, factorials actually get bigger faster than single powers of x. Okay? So it might be 100 to the power 10, but it's being divided by 10 factorial. And you'll get up to 100 to the power 1,000, but divided by 1,000 factorial, the factorials start to win, if you like. There's a tug of war between the powers trying to get big and the factorials dividing, trying to get small. And in fact, it doesn't matter what number, you could put a million in there and go up to the power of a million to a million zillion grillion, but you'd be dividing by a million zillion grillion factorial, which is huge, way too big for us to even comprehend. Okay? Now can you think about how many atoms are in the tip of that my little ballpoint pen here? Okay? All right? And how many electrons there are just around there? There'd be, even though it's small, there'd be a large number, wouldn't there? Okay? Pretty big number of electrons just in the tip of my little tiny blue tip there. Would be quite a large number of electrons. Okay? Now expand that out to how many electrons there are in this room. In all of our bodies, in all of the atoms in the air, in all of the atoms in the seat, that sort of thing. Quite a large number of electrons that we could never actually sit down and count one by one in our lifetimes or in a long lifetime. Okay? Even if we were counting one a second, we wouldn't be able to count all of the electrons in this room in our lifetime, counting one a second. Okay? Now expand that out, not from this room, but to the number of electrons in the world. Okay? That's a lot bigger, isn't it? Now, how many worlds are there? Well, go from the world to Jupiter. Jupiter's much bigger than the Earth. And go from Jupiter to the Sun. The Sun is much bigger than Jupiter. And how many suns are there in the universe? Well, in this galaxy, in fact. How many suns are there in the galaxy? How many galaxies are there? Okay, so how many electrons are there in the universe? A big number. Let me show you what that big number is about. Now, I've written that down pretty quickly, and I hope you're actually amazed at what maths can do, because that number is totally huge that we can never comprehend. Okay? Now here's another number. Does anybody know a name for that? That's a googol. Okay? Now that number is about 10 to the 19, so think of that. 10, a 1 with 19 zeros. 1 with 19 zeros. Lots of these. Okay? This was the number of electrons in the universe. So this is a huge number. So you could write, yeah, that's a number. Now guess what? So that's only one with 100 numbers after it. That's only one with 100 zeros after it. But this is one with that huge number, many more times the number of electrons in the universe. So you could never even write out the number of zeros, let alone this number. That's called a googolplex. Okay? That's a big number. That's not the biggest number we've ever used in the mathematical proof. We've actually used a much bigger number in a mathematical proof. Okay, so, just a couple more minutes for me, please. What I'm saying here is that even if you got up to this huge number, you would eventually be dividing by that number factorial, which is super huge. and coming back down to 0. So what actually happens is that this series, even though it goes on forever and ever and ever, actually converges for all values of x. You can put any number, big positive or big negative, in there, and you will always, if you go far enough, end up getting a good approximation to the exponential function. It just so happens that putting a big number in here means taking an exponential of a big number, and that's going to be big anyway. Okay? So in fact, the radius of convergence of this, now what was radius of convergence? That was the distance from the origin out to where you stopped and the formula didn't work anymore. So this formula works for all values of x, so the radius of convergence here is infinite. Similarly for this one, for the cos, and similarly this one for the sine. Okay? Now I'll show you just one other thing before we finish today. You know this formula. There is a relationship between the exponential function and the cos function and the sine function. But we only, this is Euler's formula, but we only see that relationship when with the complex numbers. But it almost looks like e to something is cos something plus sine something. And if you add those two things together, you see you've got the even powers there, you've got the odd powers there. They almost add up to be the exponential function, except there's some problems with minus signs. But minus signs squared come from I, don't they? Okay? So we see a hint of Euler's formula even in those things. See you this afternoon.